Good afternoon, students. Let us start the lab class. Before starting today's experiment, I want to know whether anybody has tried out working with PSpice. Has anybody tried?
No, sir.
Nobody has tried.
Sir, the UI is a little bit confusing, that's why, sir.
What is confusing?
The user interface, sir.
Okay. But did you go through the videos which we have posted in our website? All the lab videos which we have posted. Have you gone through it?
No, sir, I didn't know we had that.
Okay.
Good. Sir,
Yeah, tell me, sir.
what is it? No, sir. I have received on Word file. The corresponding experiment YouTube link is there. So I think today we'll post. I'll post that in our group, sir, the lab group.
Okay.
Maybe that is not posted. That the YouTube links are not posted.
Okay.
So I'll post it today, sir.
Okay, sir.
We have our lab recorded videos, but the other lab benches also they have done the recorded videos. So time being, I'll post those videos.
Okay.
But our videos are also available. Some 1 or 2, 3 experiments it's available in the Google Classroom.
Okay.
Yes, sir. So students, today I will be posting a Word file, which will have the recorded video with the YouTube link of all the experiments. So for time being, you can go through this experiment what we started with PSpice, that is with the last experiment doubler and tripler, and today is the Darlington emitter flower. We can try executing in the PSpice software. Yes, sir. My turn.
Okay.
Yes.
Okay, then let us start today's experiment. But I still feel students have to put an effort either in working with PSpice or with multi-sim or with any such simulation software. There are other simulation softwares available in the internet. You can go through any one of them and try to simulate all these experiments which we are discussing. Now, for the time being, let us proceed with today's experiment. Today's experiment is simulation of BJT Darlington emitter follower with and without bootstrapping. Now, you are already familiar with this emitter follower. Emitter follower generally voltage gain is unity. This is already discussed in the theory classes. So, in the case of emitter follower, at the emitter we take the output, at the base we give the input. So, whatever signal we give at the base, the same signal comes at the emitter as far as the amplitude is concerned. So, voltage gain is V naught by VA is equal to unity. Even the voltage gain is unity, this emitter follower works like a buffer. Even though the gain is unity, voltage gain is unity, it is going to have this VCC, and through the VCC it is going to supply current, because of which its input impedance is very high and its output impedance is very low. Input impedance is actually very high and output impedance is actually very low. So that is the advantage of emitter follower. So we can always use this emitter follower as, let me move this side. we can always use this emitter follower as current gain amplifier or as buffer in the analog domain. In the digital domain, buffer means the voltage will be again reconstructed. But in the analog domain, buffer means voltage will remain the same, but current gain will be there. So that is the use of emitter follower. So today's experiment is Darlington emitter follower. Darlington is the name of a scientist who constructed emitter follower with two transistors. In the theory class, you have seen the emitter follower. It is also called as common collector configuration. That is only with one active device. Now today we will see the circuit with two active devices, and later on we will see what is the meaning of this bootstrapping. Right now I will not tell you. First let us discuss the Darlington emitter follower circuit. Later on let me tell you what is the meaning of bootstrapping. And then in both of these circuits we have to determine the gain, input impedance and output impedance. This is the simulation using PSpice. So a brief theory is there, let me read it. In electrical and electronic circuits, Darlington transistor or Darlington transistor pair is an essential component. It consists of two bipolar transistors that are connected in such a way that the current amplifies by the first transistor, then by the second transistor. The configuration of the Darlington transistor gives a much higher current gain than a single transistor taken individually. The configuration of these transistors was invented by an engineer, Sidney Darlington, from Bell Laboratories in the year 1953. So let me show you the Darlington transistor now. When we have one transistor like this, let us say this transistor's emitter is connected to the base of another transistor, and let us say the collectors are connected like this. Now, this will have, let us say beta 1, and this will have beta 2. So, now whatever is the base current here, that will be multiplied by beta 1 here. So, at the emitter of the first transistor, it is beta 1 into IB. Now, beta 1 into IB is given as the input to the second transistor, and you can see the collectors are shorted here. Collector is connected with the plus VCC there. Now, beta 1 into IB is given as input to the second transistor, and we have beta 2 here. So, output here will be beta 1 into beta 2 into IB. Okay. I'm crudely writing using the mouse. This is beta 1 into IB into beta 2. That is beta 1 into beta 2 into IB. For example, if this transistor is having a beta 100, let us say this is also having another beta 2 as 100. Let us say both transistors having the same beta. The emitter current of the second transistor will be 10,000 times larger than the input current. For example, if IB is 1 milliampere, in this case, if IB is 1 milliampere, now IE2 or the IE2 is equal to, let us say IB1 is 1 milliampere, IE2 is equal to 10,000 into 1 milliampere, that is 10,000 milliampere. 10,000 milliampere is equal to 10 amperes, which is such a large gain. 10,000 times is the gain. That is called as the current gain now. Now, because of this such configuration, this is called as Darlington transistor. So, Darlington transistor is nothing but this combination where the emitter of the first transistor is connected to the base of the second transistor and collectors are shorted. Now, in the market, we have two transistors connected in this way. A single package is available. In the sense, even though we are connecting two transistors here separately, Later on, people found out that as this connection is going to give beta 1 into beta 2 times current gain, wherever they require a very high current gain, manufacturers manufacture transistors with internally 2 transistors connected that way with the single 3 pins at the output. There are type numbers like tip 122 and tip 127, TIP 122, TIP 127, both will be having NPN as well as PNP. For example, let us say I'll write it here, let us say the package of the transistor is having only 3 pins, it's having only 3 pins, and there will be EBC, there will be emitter base, collector, and this transistor's type number, let us say, is TIP 122. When there is TIP 122, internally there are 2 transistors. The shorted collector is taken out, base of the first transistor is taken out, emitter of the second transistor is taken out. Internally there will be 2 transistors instead of we physically connecting 2 transistors separately. Along with the heatsink at the top, there will be a small hole here so that additional aluminum heatsink can be connected by means of a nut and a screw. So this type of package itself is available called TIP 122 or TIP 127, either PNP or NPN. Even in the case of PNP, PNP configuration is slightly different than the NPN configuration. In the case of PNP, it is like this. As PNP is completely complementary to NPN. In the case of NPN, base current is positive, in the sense base current is going into the transistor. In the case of PNP, base current is going out of the transistor. Base current is negative. And in the case of NPN, collector are shorted and they are connected to VCC. In the case of PNP, emitter and shorted and they are connected to VEE. Because in the case of PNP, current goes into the emitter and output is taken here at the collector. And all the currents are negative in the case of PNP. That is why later on you are going to study one more amplifier called push-pull amplifier. In the case of push-pull amplifier, PNP is connected at the top and NPN is connected at the bottom. In general, always NPN will be connected at the bottom and its emitter will be connected to ground, whereas emitter of PNP will always be connected to power supply. So this is a Darlington configuration for PNP as well. Actually, this is not called as Darlington transistor. There is a separate name for such connections. There is one more transistor connection called Zickley pair. In the case of Zickley pair, PNP and NPN both are connected in the same fashion. So I just showed you how NPN and PNP both can be connected so as to have a current gain. Now the emitter follower has reasonably high input impedance and may be used wherever input impedance up to about 500 kilo ohms is needed. We have already worked out through theory classes also, and even in the lab classes we have shown you that the normal input impedance for a RC coupled common emitter amplifier is hardly from 1 kilo ohms to 2 kilo ohms, maximum 3 kilo ohms, because of R1 parallel with R2 parallel with beta into small re. Now, in the case of this emitter follower, the input impedance can be as large as 500 kilo ohms. Now, you can compare the advantage of emitter follower with the normal RC coupled amplifier. Now, for higher input impedance, we may use 2 transistors to form what is called as Darlington pair. Let us say we want to have input impedance in mega ohms, not even in kilo ohms. Think about your mobile phone receiving power from the nearest mobile phone tower. Now the mobile phone will be transmitting power nearly for 40 watts. Whereas, the tower is going to transmit power nearly for 40 watts. Whereas in your mobile phone, when it reaches your mobile phone, it will not be even in milliwatts. It will be in microwatt. Sometimes it is in nanowatt or in picowatt. If the network strength is showing only single dot, then it means the input power to the mobile phone is in picowatts. That indicates the signal strength of your mobile operator's network when it is received by your mobile phone. So, when your mobile phone is receiving a picowatts of power, now using that picowatts of power only, network service has to be established. Which means, let us say in the mobile phone you have an antenna like this. From the antenna, initially you should have a preamplifier. This preamplifier is going to pick up the RF signal from the outside and gradually it is going to amplify. Now, when the input signal is in picowatts, naturally we require a very high input impedance for this amplifier. Because when input signal is very weak, when we use a preamplifier, the amplifier should not drain energy of the input signal itself. That is why we need a very high input impedance. When we need very high input impedance, not just 500 kilo ohms, now the input impedance should be in mega ohms. When we require input impedance mega ohms, we can use the Darlington pair. When the output is taken from the emitter terminal of the transistor, the network is referred as an emitter follower. The output voltage will always be less than the input voltage due to a drop between base and emitter, that is the AC drop. However, the voltage gain is usually approximated to 1, even though it is around 0.98. In general, we call it as unity gain. In addition, the output is having the same polarity as the input voltage, because in the case of emitter follower, there is no phase shift, as you already know. It is discussed in the theory classes. Hence, it is said to follow the input voltage with an in-phase relationship. This accounts for the terminology emitter follower. For AC analysis, the collector is grounded, therefore the circuit is actually a common collector configuration. Collector is generally called AC ground there, because it is connected to power supply. Power supply is always an AC ground. So this circuit represents high impedance at the input and low impedance at the output. It is therefore frequently used for impedance matching purposes. Whenever we have to connect two circuits, let us say the first circuit is having very high output impedance, and if the second circuit is having very low input impedance. Let us say we have two circuits like this. Let us say one amplifier we have, one more amplifier we have. And let us say here Z0 is high. And let us say here Zi is low. Now, when Z0 is high and here when Zi is low, this cannot be directly connected here. Why? Because maximum power will be transferred from one circuit to another circuit only when impedances are matching. Now, in this case, there is a high output impedance, low input impedance, and there is no matching of impedance. We can connect the emitter follower here now. Whatever is our circuit, we can connect it here. Now, emitter follower will have a very high input impedance. It will have a very low output impedance. That way, these two circuits are connected together and maximum power can be transferred from the first circuit to the second circuit. That is what is meant by impedance matching, where a load is matched to the source impedance for maximum signal transfer through the system. Now, the Darlington connection shown is a connection of two transistors whose result is a current gain, that is the product of current gains of the individual transistors. I have already told you it is beta 1 into beta 2. Hence, the Darlington pair operates on one super beta. That means there is a big beta, capital beta is equivalent to, it is not capital beta, bigger beta. Bigger beta is equivalent to small beta 1 into small beta 2. This way we call it a super beta transistor offering a very high current gain when it is given in a single package. Thus, the Darlington emitter follower has the following characteristics. Voltage gain is almost unity, current gain is very high, a few thousands. Input impedance is high, hundreds of kilo ohms, sometimes mega ohms. Output impedance is low, tens of ohms. Let me show you the circuit diagram now. Let me zoom out slightly. Now, this is the circuit diagram of the Darlington emitter follower, where you can see this is a voltage divider biased emitter follower, we can say. At the input, you can see the voltage divider bias using a 68K and a 180K. The Q1 transistor is biased. And as you already know, the emitter of the final transistor must be having about half of VCC. Now here VCC is 12 volts. So here, when the AC signal is not given, theoretically we require around 6 volts at this point. At this point we require 6 volts, that is half of this 12 volts. So that 6 volt DC is across R1, remaining 6 volts is across Q2 itself. Q2 is operating in the active region now. Now when signal is applied, the same signal is coming here, and then the same signal is coming here. In the same phase, you can see base to emitter, there is no phase shift. Again, base to emitter, there is no phase shift. But here there is beta 1 and beta 2. Total current gain is beta 1 into beta 2. Now there can be a coupling capacitor connected at the output, which will block the 6 volts DC and it will pass AC to the output. We can connect one load resistance at the output, for example 1 kilo ohms, and the emitter resistor is 1.5 kilo ohms. And you can see both the collectors are connected directly to the supply because there is this resistor at the emitter. So this will have around 6 volts across it, and this also will have around 6 volts across it. 6 volts plus 0.7. Actually, Q1 will have 6 volts plus 0.7 because there is VBE here. You can see when the total drop here is 6 volts. Now the 6 volts comprises of the base to emitter potential at this path, at this branch. So across Q1, it will be actually around 6.5 volts to 6.6 volts to 6.7 volts, depending upon the VBE of Q2. Now both the transistors will be operating in the active region. So this is the Darlington emitter follower, and students have to perform simulation here. You can see 12 volt DC is connected to the collector and a 1 volt AC. Unlike all other amplifiers, we are giving the input in volts, not in millivolts. Why? Because the gain is unity. When the gain is 1, you give 1 volts here, you will get the output also approximately 0.98 volts or 0.99 volts, approximately 1 volt. Now you can see that PSpice's notations given here. When the circuit was edited in PSpice, already PSpice has shown the DC voltages there. You can see 12 volts is shown here, and here 7.41 volts is shown. Ideally, it has to be 6 volts, 12 volts by 2. But practically, by the biasing of these two resistors and because of the design tolerances, there is 7.4 volts here. So still 7.4 volts means still Q2 is in active region only. 12 minus 7.4 is around 3.6 volts, right? No. 12 minus 7 is 5. So 12 minus 7.4 is 4.6 volts. Around 4.6 volts is across Q2. That means it is under active region. Similarly, you can see here it is 7.4, here it is 8.118. Approximately 7.4 plus 0.6 is around 8 volts. So the emitter of the first transistor is at 8 volts, upper side it is 12 volts, which means even Q1, across Q1, there is 4 volts, which means it is in active region. Now you can see at the base it is around 8.69 volts because 8 plus 0.7 across base and emitter. So because of this voltage loader bias network 68K and 180K, here we are getting around 8.7 volts. So PSpice shows all these DC values. Later on you have to apply 1 volt AC, 0 volts DC, means the input signal should not contain any DC component. It should be pure AC. You apply 1 volt here, you will get the same 1 volt here at the output. But how do you measure the input impedance? Anybody remembers how to measure the input impedance? Any students, do they remember how to measure the input impedance? As no one is responding, let me tell you once again about how to measure input impedance. Now, inside the amplifier, you have Zi, right? Let me remove this. Inside the amplifier, you will have Zi. This is now Zi. So outside the amplifier, you should connect one decade resistance box and you have to apply input voltage. You have to apply input voltage. And let us say you apply input voltage 1 volt at the input, 1 volt at the input. Initially, when this decade resistance box or the variable resistance box, when it is at 0, you will get 1 volt only here. Now you will have to keep on increasing this resistance at the input so that at the output you will get around 0.5 volts. Until you get 0.5 volts, you have to keep on increasing the value of this decade resistance box. So when you get 0.5 volts, it indicates that this resistance and this resistance both are equal because it is working like a voltage divider network. Input impedance is inside the amplifier. Now we have to somehow measure it. So externally we connect this resistance box, and when we get output of 0.5 volts, then it means 0.5 is across this, 0.5 is across this. Naturally, when two voltages across the two resistors are same, naturally values are also same, currents are also same. So that is how we conclude that the value of the external resistance, which is giving us 0.5 volts output, that is the input impedance of this amplifier. Similarly, for measuring output impedance, the reverse is done. At the output, the same decade resistance box is connected in parallel to ground, and initially it is kept at maximum. Otherwise, if it is connected to 0, all output will go to ground and the amplifier output will be short circuited. That should not happen. That is why the decade resistance box is connected at the output directly to the ground with the other end, and initially it is kept at maximum value. Gradually it is reduced until output becomes again 0.5 volts. At that time, at the input, this decade resistance box is not necessary. We are directly giving the 1 volt to the amplifier. And at that time, you know that Z0 is in series and output resistance will be in parallel now. When those two equal their value, the value at which we get 0.5 volts is the output impedance of the amplifier. This is how we measure the input and output impedances of the amplifier, and we will have to follow the same procedure here also. Even though this is PSpice, even in PSpice you can do the same thing. Even in PSpice also, here you can connect a variable resistance. Here itself. Here you can connect a variable resistance and then initially keep it at 0 and keep on measuring the output here, and you keep on increasing the value to some value later on, and you keep on measuring the output. Whenever, for whichever value of the input resistance, when the output becomes 0.5 volts, then the value of this resistance itself is input impedance. Similarly, you have to follow output impedance where you have to connect, instead of this 1K load, you can directly connect one variable resistance here. In the PSpice, variable resistance is also available. That variable resistance can be connected and it can be varied to measure the output impedance. In this manner, we are going to measure the input and output impedances. Now, this is the Darlington emitter follower. Next, let us move on to bootstrapping. Darlington pair circuit with bootstrapping. What is the meaning of bootstrapping? Boot means what? We are all wearing shoes. Shoes are also called as boots. Bootstrapping means what? Generally, to the boot there will be a strap or there will be a lace. If it is not a pump shoe or a slip-in shoe, there will be a lace or a strap. And what is the purpose of strap? Strap is to tighten. Or what is the purpose of lace? Lace is to tighten, so that the boot will be firm and the feet will be within the boot. The foot will be within the boot. Okay. So the meaning of bootstrapping is to tighten the conditions or to improve the conditions. Tighten the conditions in the sense to have betterment. Somehow somebody related that term here in our circuit. The circuit has nothing to do with boot. The circuit has nothing to do with strap. Still, bootstrapping basically means tightening the conditions. Maybe the scientist who was working with such conditions, maybe his boot was loose. I am having a funny imagination that way. Maybe the scientist his boot was loose, and when he was tightening his boot, he got the idea about how to increase the input impedance further. So maybe because of which they started calling as bootstrapping. There are many such incidents. Why do they call the Bluetooth technology as Bluetooth? There are many such incidents. In general, Bluetooth is meant for people consuming blueberries. Somehow, when they consumed blueberries, somehow they kept the name Bluetooth. Similarly, why do they call the Java programming language as Java? Those scientists were having a coffee in Brazil, and when they were drinking coffee, they got the idea of that particular language. And in Brazil, they call coffee as Java. So they named the language as Java. That way, there are many such things. Even why do we say hello when we pick up a call? Hello was used by Alexander Graham Bell. Because Alexander Graham Bell used hello, everyone else is using hello now. So there are many such funny things in the technology also. So that is how the term bootstrapping came into existence. Now the meaning of bootstrapping is what? Meaning of bootstrapping is tightening the conditions or improvising the conditions. Now you can see there is the regular Darlington transistor. There is a small mistake here that I will tell you later. You have the regular Darlington transistor with this resistance and this resistance. The mistake is there is no dot here. There is a direct connection. Let me write it directly with a different color. See, there is no dot here. Let me use the pen tool only. There is no dot here. There is a direct connection. Okay. Whereas here, everywhere you have a dot. I'll tell you what is this circuit later on. Now, this R3 is connected to the R4 junction and R4 is 180K. Now here you will have one more resistance 10K from which the base current is coming. That means the base current to Q1 is coming through 68K and 10K. Okay. And that base current is going from the emitter to Q2. That is the base current of beta 1 into beta 2. And we already have this R1 which was there earlier also. This one was the load 1K and we had a coupling capacitance here. All other things are the same. Only difference here is this connection. The difference here is output is connected to one more capacitor which is large value 10 microfarad. You can see here the coupling capacitor is only 0.47 microfarad, where here it is 10 microfarad. And the 10 microfarad is connected to this junction of this 10K, 68K and 180K. 68K and 180K are the biasing resistors to the Darlington circuit or to the emitter follower circuit. But this 10K or this R6 is an addition and 10 microfarad series capacitance is an addition. Now this circuit is called as a bootstrapping circuit. There is a lengthy mathematical analysis for this circuit, but we are not keeping it in the syllabus as such because unnecessary mathematical derivations need not be dealt with. It is only for the people who are really interested in studying them. Scientists have already done that work and it is available in the textbooks. In the theory class or in the lab, we have not kept those lengthy derivations because it is an unnecessary wastage of time in deriving all those things. So, our curriculum is mainly for making you to understand the functionalities of the circuits, not to get into the serious mathematical computations. So, even this Darlington pair with the bootstrapping can be approached with the AC analysis. And once we perform the AC analysis, finally, the input impedance of the circuit is going to be increased just by the connection of these two devices. Those students who are interested to know more about how this input impedance increases by the connection of these two components, as far as the AC analysis is concerned, you can go through the book Electronic Devices and Circuits by Millman and Halkis. It's a very old book. It has gone through many editions. Even now the book is available. You can go through it just to have an idea about how AC analysis is performed for the circuit and how input impedance increases. I'll tell you in brief what happens here. In brief, I'll tell you. I'll not get into the mathematical analysis. Let us say we have this. Let me erase this. Let us say we have this input signal. When you have the input signal that is coming here and the same input signal is coming here, right? We know this. We have this input signal here. Let me write neatly to some extent. And the same input signal is coming here with the same amplitude. 1 volt only. Even though you find a light difference, ignore it because I am writing through the mouse only. Now you can see when this is having a positive cycle here, that positive cycle is coming here. And that positive cycle is passing through this capacitance. And there is this resistance here. Now, already we have an output here. And that output is fed back here. And it is fed back here. Now we have this input phase and this output phase are almost same, right? You can see the phase of both the signals is same because emitter follower is not going to give any phase shift. But amplitude wise, I should say, let me write it here, let me write it here. Amplitude wise, even though we say it is unity gain, it will not be unity gain. It will be 0.98. So when it is 0.98, if input is 1 volt, here the output will be 0.98 volts. When there is 0.98 volts, here it is 1 volt. Now 1 volt and 0.98, that is a 0.02 volts difference between these two. Between this node and this node, there is a 0.02 volts difference. That 0.02 volts is appearing across 10K. Okay. 0.02 volts is appearing across 10K. So across 10K, what is the current? Across 10K, the current is 0.02 volts divided by 10,000. Now 0.02 volts divided by 10,000 is how much? 0.002, or let me write directly. I am giving an input of 1 volt only. So for the 1 volt, there is a 0.02 volts drop across this. When there is a 0.02 volts drop across this, 0.02 volts divided by 10K is there here, no? That is the bootstrapping connection. So 0.02 divided by 10,000. 0.02 divided by 10 is 0.002. 0.002 milliampere. 0.002 milliampere is 0.002 milliampere is 2 microampere. Now, what is the conclusion here? Conclusion is there is a feedback of 2 microampere current in the AC domain. We are feeding AC signal, we are getting back the AC signal. Even though this looks like a positive feedback because the phase is same. But positive feedback is not going to increase the gain here, right? Amplifier gain is unity here. It will not become an oscillator now. You might be thinking that because of the positive feedback, the circuit will become oscillator. If oscillator has to work that way, A beta must be equal to 1, right? The A amplifier gain must be much larger. But amplifier gain here is unity. So this will not work like an oscillator. But the only thing is, across this 10 microfarad and 10 kilo ohms, there is a 2 microampere AC feedback. Let me remove this 0.98 now. Okay, there's a 2 microampere AC feedback. And that 2 microampere AC feedback itself is going to have very high input impedance that way. Now you can see R3 and R4 are used for DC biasing of Q1. When compared to 68K, this 10K is a much lesser value. But the increase in the input impedance depends on this particular 10K itself. Even though it is 10,000 ohms here, as far as DC is concerned, as far as AC is concerned, you can see its effect. It is mainly because of this 0.02 volts across it. There will be no voltage drop across 10 microfarad. Why? 10 microfarad is going to give a very less reactance. X equals 102 pi FC. When C is very high, X is very low. So across the capacitor, there is no drop at all. It is all across this resistor. But this capacitor is going to give a AC feedback only, purposefully. DC should not come here. It is meant for AC. That is why capacitance is connected in series and the resistor is connected in this fashion. So this type of connection is called bootstrapping connection. Just one resistor and one capacitor. By means of this bootstrapping connection, input impedance will be having a larger value. But output impedance will be the same as the previous circuit. We are not doing anything for the output impedance as such. Output impedance is anyhow going to be very low in this circuit because of beta 1 into beta 2. But we want to have still more input impedance, means we can go for this bootstrapping connections. So the procedure is place the components and make the connections as shown in the circuit in the PSpice, apply sinusoidal AC voltage of 1 volt, perform AC analysis and select the logarithmic graph for a start frequency of 100 Hertz and ending frequency approximately 100 megahertz with points per decade as 50/100. Now, in the last class, I think I have told you already, there are two types of analysis called transient analysis and AC analysis. We perform transient analysis to check the shape of the output waveform and to observe the waveform as such. Whereas we perform AC analysis to find out the bandwidth and the gain. Now, in the AC analysis, you can select a logarithmic graph. It is as if you are taking a semi-log graph sheet and x-axis is frequency and y-axis is voltage gain. It is same as that, even in PSpice. That is what is called as AC analysis now. So select the logarithmic graph. Starting frequency can be 100 Hertz, ending frequency can be around 100 megahertz, and points per decade can be 50/100. That is the roll-off factor, or for the graph sheet, what all points you want to have. Now observe the frequency response curve of BJT emitter for with and without bootstrapping. You can measure the gain also, you can measure the bandwidth also there. You will have a very large bandwidth there, and gain will be almost equivalent to unity. Later on, you can measure the input impedance. Connect a variable resistance in series between VAC and input capacitor. As I have shown you already, increase the resistance value such that the output voltage reduces by half of the maximum output voltage. Corresponding resistance value is the input impedance. I had shown you already, it behaves like a voltage divider network. But you have to connect a variable resistance which is available in PSpice. Now to determine the output impedance, connect a variable resistor in parallel across the load resistor. Set the variable resistor value 10K. Now the load resistor also can be there in parallel to the variable resistor, because anyhow output impedance is going to be very low. So it is going to drive the load resistor also. Now reduce the resistance value such that the output voltage reduces by half of the maximum voltage. Corresponding resistance value is the output impedance. But my suggestion would be, you remove the load resistor and then connect this variable resistor across the output. Why? Can anybody tell me? Why am I telling you to remove the load resistor and connect the variable resistor at the output for measuring output impedance? Can anybody tell me? I am asking you to remove this 1K, then connect the variable resistor here. Why am I telling that? Can anybody tell me? Okay, the answer is, if already this 1K load resistance is there, then you connect that, always the output impedance is much lesser, it is in few ohms. Now this 1K comes in parallel, 1K is inclusive of the output impedance there, isn't it? Why should I have this 1K? So remove the 1K. If you connect 1K, there will be a slight inaccuracy when they come in parallel. Even though the inaccuracy may be in the order of only few ohms, still it matters. So it is better that you remove the 1K and connect the variable resistance. It will accurately give you the value of output impedance. Later on, the load can be connected once again. That is the answer. Now with that, you can see frequency response of the Darling-Tartar circuit without bootstrapping. You can see input is 1 volt, output is slightly less than 1 volt, around 0.98 volts I can say, because this is 0.8 and there are 4 divisions, 0.825, 0.85, 0.875 and sorry, it is 0.8, this is 0.9, 0.85, 0.9, 0.95, 0.95, 0.96, 0.97, somewhere around 0.98. That is the maximum voltage here. You can see after about 10 megahertz, it is slightly reducing. It will keep on reducing later on. When you plot the curve, you can still increase this frequency beyond 100 megahertz also you can, and you can actually try to measure the bandwidth. Now what is bandwidth? maximum voltage into 0.7. Now let us say this is 1 volt, 1 volt into 0.7. We have to see where it is coming down. Here it is 0.6, here it is 0.7. It has not yet come down. So we can say slightly above 100 megahertz, it will touch to 0.7. That way we can say the bandwidth of this circuit without bootstrapping is around 100 megahertz, we can say. Now the frequency response with the bootstrapping. With the bootstrapping, you can see there's a slight improvement because of that positive feedback. There's a slight positive feedback there, right? Because of the positive feedback, the input signal is slightly increased. Gain has become now 1 only instead of 0.98. Gain has become 1. But you can see the gain is not reducing here. It was supposed to reduce here, right? Without bootstrapping, it is reducing here. But with the bootstrapping, gain is not reducing, gain is continuing. Which means with the bootstrapping, even input impedance is also increased and the bandwidth is also increased. That is the idea. Now with that, I have come to the end of today's class. If people have any questions, you can ask me. Okay, if people have no questions, now the meeting will be on. You will have to write the observation book for today and you will have to upload into the Google class. Prithviraj sir?
Yes, sir.
Can you create one assignment in the Google class?
Yes, sir. I will create it, sir.
Okay.
Already last week we have created for experiment 6 voltage multiplier, sir. So today around 16 students have turned. All
Okay.
the 16 students have uploaded.
Okay.
So today I'll create it as experiment 7 Darlington amplifier, sir.
Okay. Okay, students, meeting will be on, but we will remain
Sir,
muted.
there is one more.
Yeah.
Yes, sir. Students, there is one more thing. Beginning, I was telling about the YouTube link. Already, the drive link of the till now we have 7 lab sessions. So all the 7 lab sessions, the drive link was shared in the Google Classroom. Already, sir has uploaded it, put it in the stream. And I also sent just now that YouTube link of the experiments which has been done by the different teachers, by the different lab teachers. So that involves the hardware, how it is being connected, and that is also sent as a Word file. So there we have 2 Word file I'm going to send. One is already it's being sent of the YouTube links, and the other one YouTube link, another Word file will have the drive link of the previous lab sessions. Although it is sent in the Google Classroom, I'm going to send another Word file of all the previous lab sessions, classes of our batch. Yes, sir. So it is being already there available in Google Classroom, sir.
Okay, sir.
Yes, sir.
So students, you upload your observation book PDF into the assignment. We will remain muted, but meeting will be on. As and when you complete your submission into the Google class, you can leave this meeting. I will be muting myself and I will be stopping the recording also.